Hello, everyone. I'm worried this will take a little bit longer than normal, so I am going to go through this probably in two videos. I did post you a highlight note. Let's see. Here, bare minimum, if you guys can just look over this, my handwritten stuff here. This is supposed to be a 13. I thought it looked like a B. I was worried. This is the highlights of stuff you need to know. But I'm going to go through this right now. There's my work for it all the way complete. But it's a little bit longer section. But there's a lot of review on it too. So this is all review. This first page is all review. Basically, they're reminding us of what this fundamental theorem of algebra says. It says the degree of the polynomial tells you how many roots there are. Now, some of us are confused about the difference between roots and x-intercepts. There's not a lot of difference really, except it's x equals for a root. You can just tell me what x equals, and they can be imaginary. And then x-intercepts, you would write like the number, comma, 0, and those have to be real. But roots can show up as x-intercepts if they are real. So that's what this is going to discuss here. The first thing they want to know is what type of roots they are and then to actually find them, real or imaginary. So this one, I'm looking for 2. I know I'm looking for 2 because the degree is 2 and I can see them, and that's at -3 and 2. So types of roots are real. What are the roots? They are -1, -2, -3, and 2. Okay, now this one looks like, yeah, I got some in-betweeners. They're definitely real. They are real. I can see them. If you can see them, they are real. But I'm going to have to do some math here. You can do quadratic formula. I did on the notes a refresher on completing the square. Remember, that was sometimes easier if this B term was even. If I was going to draw the boxes, I'll draw the boxes here. I have -2x, so that would be 1 on each side. Okay, so the closest box this guy is to is an x minus 1 square. That would put 1 in the corner. That would put 1 in the corner, but I have -7, so I'd have to subtract 8. And you can see that here, the vertex is 1, -8. You can actually see it, so you could have shortcutted that as well. Now to find the roots, we will have to solve. We will add 8 to both sides. X minus 1 squared equals 8. Square root both sides. You'll have to clean this one up. So that's an x minus 1 equals, that's 4 times 2, or 2 root 2, plus or minus, don't forget. And then add 1. So the 2 roots are 1 plus 2 root 2 and 1 minus 2 root 2. Okay, again, that is review from way back at the beginning of the year. This is a real root as well. I can see this one. Now this one is showing up as a bounce, so we call that multiplicity 2, or a double root, and this root is at 2. That root is at 2. Now this one I cannot see, so because I cannot see the x-intercepts, these will be imaginary roots, or complex probably would have been better for me to say. And I can use a shortcut because I can see the vertex, but just the refresher, it'll be an x minus 2 squared, which would put a 4 in the corner, but I have to get to 5, so I will add 1. Right 2 up 1, that's what the vertex is. When I go ahead and solve it, I will subtract 1 from both sides. X minus 2 squared is -1. Square root both sides. Don't forget, the square root of -1 is, that's what the I is, plus or minus I. It's been a minute since we talked about that. Add 2 to both sides, and my roots are 2 plus I and 2 minus I. Okay, now the next page is going to have us use those ideas. So did they all have 2 roots? The answer is yes, even though the one had a double root. So it did follow. The double root does count twice. So that they did all have the fundamental theorem of algebra. How did you do this? You could look, you could factor. You could have factored this first one, or you could complete the square. Okay, so you can adjust that. And now they want us to use your work from problem 1 to write these in factored form. So this one I can just go ahead and factor. If I factored it, it would be x plus 3, x minus 2. And don't forget that the roots come from changing the signs of those factors, which is -3 too. So I could have worked in reverse, or I could have just factored it. Now this one I cannot factor, so I'm going to have to use my work from my last guy, which I already just turned the page here. It was 1 plus 2 root 2 and 1 minus 2 root 2. So I'm going to write this as factored form, which will be x minus parentheses 1 plus 2 root 2 and x minus parentheses 1 minus 2 root 2. They want you to check this by graphing. You can plug that one into your calculator, but you'll know it's right because I just told you it was right. You could distribute the minus. You could have had x minus 1 minus 2 root 2 as your factors and x minus 1 plus 2 root 2 as your factors. Those are the same thing. Now this one is a double root, and we could have factored it right away. This is just x minus 2 squared. The root is 2, but it comes up twice, which is why there's an exponent here. And then this one, the roots were 2 plus or minus I. So you could put x minus parentheses 2 plus I. You cannot graph this one, I don't think. X minus parentheses 2 minus I. That's how I would write it. Or you could distribute and say x minus 2 minus I and x minus 2 plus I. Okay, so now, would you say that the roots are the same as x-intercepts only when they're real? I would say that's only if they are real. The difference is how you express it. Remember, x-intercepts are ordered pairs. Roots are x equals a number. So it's kind of the same information, but it's not the same. And only if they're real. What else do we got here? Problem 4 is relation to roots and factors. Well, if you have a root, if x equals the root, then x minus parenthesis the root is the factor. So that's a factor, and that's the root. So you can find them written with each other. Okay. I think I'm going to end this video now. We're going to talk about these cubics because that was mostly review.